Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll take a deep dive into one of the most critical aspects of managing relational databases in the cloud, backups and snapshots in Amazon RDS. We'll break down the core differences between automated backups and manual snapshots, walk through how they work under the hood, and explain when and why to use each. You'll learn how RDS handles data durability, point-in-time recovery, and disaster recovery using incremental, storage-efficient techniques. We'll also explore best practices for managing backup retention, security, cross-region strategies, and automation for backup lifecycles. Let's get started. Amazon RDS, which stands for Relational Database Service, is a fully managed cloud database solution from AWS that takes care of the heavy operational lifting so you can focus on building applications. Traditionally, managing a relational database meant handling everything from server provisioning and software patching to backups, monitoring, and scaling. With RDS, AWS abstracts all of that complexity by offering an out-of-the-box solution that automates these essential tasks. One of the biggest advantages of RDS is its simplicity. You can launch a production-ready database in minutes using the AWS Management Console, CLI, or SDKs. You're able to choose from multiple popular database engines, including MySQL, PostgreSQL, MariaDB, Oracle, and SQL Server, all without having to manually configure or maintain the underlying infrastructure. When it comes to scalability, RDS allows you to independently scale compute and storage resources. Whether your workload needs more CPU power or additional disk space, you can scale vertically with minimal downtime, helping you meet growing performance demands without service disruption. For mission-critical applications that require high availability and failover protection, RDS offers multi-AZ deployments. This means your primary database is automatically replicated to a standby instance in another availability zone. In the event of a failure, RDS automatically fails over to the standby with no manual intervention, minimizing downtime and maintaining business continuity. RDS also supports automated backups and manual snapshots. Backups are retained for a user-defined retention period and enable point-in-time recovery, ensuring that data loss is minimized in the event of an accident or issue. Snapshots can be created at any time and retained indefinitely for long-term archival. For performance tuning and optimization, RDS provides powerful tools like read replicas, which allow you to offload read-heavy traffic from the primary instance, improving throughput and scalability. You can also integrate your RDS environment with Amazon Elasticache to cache frequent queries, reducing latency even further. And with Performance Insights, you get a visual dashboard that shows exactly where your database load is coming from, helping you diagnose bottlenecks and optimize query performance over time. In today's cloud-native, data-driven world, backups are no longer just a checkbox. They're a strategic pillar of resilience, governance, and compliance. We begin with the RDS backup maturity model, tracing the evolution from basic automated snapshots to enterprise-grade architectures involving multi-region replication, point-in-time recovery, and backup vaulting, designed not just for availability, but for survivability. Next, we go beyond default backup settings. While AWS provides solid baseline capabilities, enterprise workloads often demand tighter RPOs, longer retention, encrypted cross-account copies, and tighter integration with organizational recovery objectives. Defaults are convenient, but rarely sufficient. Backup as a component of data governance is where strategy meets accountability. Backups should align with data classification, retention policies, audit trails, and lineage tracking. It's not just about storing data, it's about managing it responsibly. But there's a trade-off. Every backup method, whether snapshot, logical dump, or bin log shipping, carries performance implications. We'll dive into how to quantify the I/O and throughput impacts, and mitigate them using off-peak windows, read replicas, or staggered schedules. From a compliance perspective, RDS backups must map to frameworks like SOX, HIPAA, and GDPR. That means encryption at rest, immutability, audit logging, and the ability to demonstrate recoverability within specific SLAs. Then comes the total cost of ownership. Snapshots may seem cheap, but cross-region replication, long-term retention, and operational monitoring add up. Knowing where costs accrue is key to avoiding budget overruns. Finally, a backup strategy is the bedrock of disaster recovery. A well-architected RDS backup design defines how quickly and how completely you recover from catastrophic failure. Recovery isn't luck, it's the result of architecture by design. When it comes to protecting relational data in the cloud, understanding how backups work is just as important as knowing that they do. First, we compare storage volume snapshots versus logical backups. Snapshots are block-level images, fast, consistent, and storage efficient, captured directly from the underlying EBS volumes. Logical backups, on the other hand, are SQL dumps. Portable, human-readable, and ideal for selective restores, but far slower and more resource-intensive. The efficiency of snapshots is powered by copy-on-write code technology. Instead of duplicating entire volumes, CUDA tracks changes at the block level. This drastically reduces snapshot times and storage footprint, enabling frequent backups without penalizing performance. To enable point-in-time recovery, RDS doesn't just capture snapshots, it tracks binary log positions. These transaction logs serve as the delta stream, allowing precise recovery down to the second by replaying operations between snapshots. Incremental or differential backup mechanics further enhance efficiency. Rather than recopying unchanged data, RDS tracks modifications at the storage layer, optimizing both backup time and storage consumption. Beneath each snapshot lies a snapshot metadata structure, invisible to users but critical to AWS. This metadata maps dependencies, retention rules, and backup lineage, allowing AWS to manage multi-generation snapshots safely and cost-effectively. During backup operations, storage is dynamically allocated for temporary data structures and logs. Knowing how and when AWS charges for that space, especially across regions, can help you fine-tune both performance and cost. Finally, concurrency control ensures your workload stays responsive. RDS intelligently throttles I/O, avoids long locks, and uses multi-threaded operations to minimize the impact on production databases, even during intensive backup cycles. In any serious RDS backup strategy, knowing the difference between what's automated and what you must control manually is vital. Start with the basics. Automated backups in RDS offer convenience, but they max out at 35 days of retention and are subject to AWS managed lifecycles. For anything beyond that, like regulatory requirements or long-term rollback points, manual snapshots are your strategic fallback. But with freedom comes responsibility. That's where tagging strategies come in. Design a consistent tagging taxonomy, like project, owner, retention period, and environment, to make manual snapshots searchable, auditable, and manageable at scale. Pair that with snapshot naming conventions. Think beyond db-snapshot-1. Instead, use patterns like appname-invive-date-purpose to enable automation and eliminate ambiguity. When snapshots are named intelligently, scripting and lifecycle actions become far more predictable. A powerful use case for manual snapshots is the pre-change snapshot, an event-driven safety net triggered before schema changes, patching, or large data migrations. These snapshots are developer-initiated and tightly coupled to release workflows, providing instant rollback capability. Of course, cost optimization is key. Manual snapshots persist until deleted, and duplicated snapshots across regions or time can balloon costs. Periodic audits and deduplication routines keep storage usage and your bill under control. But a backup is only as good as its ability to restore. That's why automated testing of manual snapshots is crucial. Implement routines that spin up temporary test environments from snapshots to validate integrity and recovery readiness. Finally, don't keep all your eggs in one region. Build pipelines for cross-region snapshot copy automation, ensuring your manual snapshots are geographically distributed and resilient against regional outages or data loss. In a globally distributed architecture, multi-region backup strategies aren't just an enhancement, they're a necessity. They ensure your data is protected, and designing them effectively requires a balance of performance, compliance, and cost. Let's start with cross-region snapshot copy optimizations. Copying snapshots between AWS regions can introduce latency and cost. Use techniques like snapshot compression, deduplication-aware workflows, and scheduling during low-demand periods to minimize both transfer time and egress fees. Next, consider asymmetric retention policies. Not every region needs the same backup lifespan. Your primary region might keep 7 days, while your secondary retains only critical monthly or quarterly backups, significantly reducing storage cost while preserving resiliency. Regional compliance variations are critical. Data sovereignty laws like GDPR or Australia's Privacy Act can dictate where data can reside and for how long. Your backup architecture must be dynamic enough to adapt based on jurisdictional boundaries and legal mandates. When considering backup sources, analyze read replica backups versus direct snapshots. Backing up from read replicas offloads the primary, but comes with consistency considerations. It's a trade-off between performance isolation and data integrity guarantees. For enterprise-scale, global backup orchestration is a must. Build centralized control planes using AWS Backup, Lambda, and step functions to uniformly manage policies, lifecycles, and audits across all regions and accounts. RTO isn't universal. Set regional recovery time objectives based on the business importance of each workload. Some applications may require near-instant failover. Others can tolerate a delayed recovery path. Finally, dive into the data transfer cost models. Inter-region data movement is chargeable by GB per snapshot. Use budget alerts, tiered retention strategies, and monitoring to ensure you're not bleeding cost in the name of resilience. Point-in-time recovery, PITR, is one of the most powerful capabilities in RDS. But to truly harness it, we need to go beyond the checkbox and into the architecture. Let's explore advanced PITR techniques that elevate your recovery strategy from functional to fault-tolerant. It starts with strategic backup window placement. Backups don't happen in isolation. They run alongside live workloads. Aligning your backup window with natural dips in traffic ensures minimal performance impact and more consistent snapshot baselines for PITR anchoring. Next, consider transaction log retention. Binary logs accumulate fast, and while longer retention increases your recovery range, it also drives up storage costs. Fine-tuning these settings based on RTO/RPO needs and the actual volatility of your data is key to a cost-effective PITR strategy. But what good is a recovery window if you're not sure it works? PR verification testing is essential. This means regularly spinning up temporary instances from specific recovery points, validating data integrity and business function continuity without disrupting production. For critical systems, cross-region PR ensures that even a full regional outage doesn't compromise your recovery. By replicating snapshots and logs across regions, you extend PITR into a geographically resilient disaster recovery framework. With multi-AZ deployments, PITR has added complexity. Transaction logs are shipped across zones, and the standby replica plays a role in maintaining recovery consistency. Understanding how AWS manages this behind the scenes is crucial for precise failover and restore logic. And finally, ensure your PITR chain is valid. Gaps in binary logs due to misconfigurations or storage issues can break your recovery timeline. Regular integrity checks and alerts on log shipping anomalies protect against silent failures. This illustration captures the backup workflow that powers Amazon RDS point-in-time recovery, or PITR, a feature designed to give you precise control over database restoration. At the start of the timeline, the process begins with a full backup of your RDS database. This is visually represented by a stack of disks labeled Full Backup. This snapshot captures the entire state of your database at a given moment and serves as the foundational starting point for future recovery. Following the full backup, log backups are performed at regular intervals. These are depicted as smaller disks labeled Log Backup and are used to track every transaction or change made to the database after the initial full backup. Think of them as a journal that records every detail needed to replay database operations over time. As the timeline progresses, new full backups are taken periodically, each followed by its own sequence of log backups. In the illustration, these sets of backups are color-coded to distinguish their purpose. The blue-colored full and log backups specifically support point-in-time recovery. This means you can restore your database to any exact moment within this PITR window, whether that's 10:03 a.m. yesterday or 5 minutes ago, by combining a full backup with the relevant sequence of transaction logs. Outside the PITR window, the system retains only the backups required to meet your overall retention policy, shown here in yellow. These backups allow you to restore your database to the point when each backup was taken but they don't support arbitrary time-based recovery like PITR does. At the bottom of the diagram, a continuous series of log backups further illustrates this concept. A green arrow labeled Data Restoration to Any Point Within PITR emphasizes your ability to roll forward to any second in time, offering the granularity and precision critical in disaster recovery scenarios or user error correction. When it comes to RDS backups, encryption isn't optional, it's foundational. We begin with KMS integration for snapshot encryption. When RDS snapshots are encrypted, they're bound to a KMS key, either AWS managed or customer managed. This encryption extends to all automated and manual snapshots derived from that instance. Key rotation is supported, but it's not automatic for existing backups, requiring careful planning to avoid access issues during recovery. Moving data across regions. Snapshot encryption during cross-region copies is handled intelligently by AWS, but you must ensure the destination region has access to the same KMS key or provide a new key with aligned permissions. Misconfigurations here can silently block disaster recovery workflows. For enterprises with multiple accounts, cross-account backup sharing with encryption demands precise control. You must explicitly grant access to both the snapshot and the KMS key, ensuring tight scoping with IAM and KMS key policies to avoid unintentional exposure. That's where IAM permission boundaries become critical. Design least privilege roles that allow snapshot creation, sharing, and deletion without over-permissioning access to unrelated resources or keys. Backup automation should never compromise your security perimeter. Encryption material rotation strategies should be well defined. While KMS supports key rotation, existing snapshots tied to older keys won't retroactively re-encrypt. Plan periodic re-snapshotting or data refresh cycles to align with evolving security baselines. Don't forget the metadata. Protecting backup metadata, like timestamps, tags, and dependency trees, is crucial. This data can be exploited to map infrastructure if exposed. And finally, backup security in transit. AWS uses TLS for data in motion, but understanding which operations cross regions or accounts and ensuring those channels are encrypted end-to-end is key to airtight backup hygiene. This illustration walks us through the secure process of sharing an encrypted Amazon RDS snapshot across AWS accounts, typically from a production environment to a separate QA or staging account, and restoring it as a new database instance. We begin in the customer production account, where a live database instance is running. At a certain point, a snapshot of this production database is taken. Because the database is encrypted, the resulting snapshot is also encrypted using key managed through KMS. To share this encrypted snapshot with another AWS account, let's say a QA or staging environment, specific steps are required to maintain security. First, the encryption key itself must be updated to allow the receiving account to access it. This means modifying the key policy in AWS KMS to grant decrypt permissions to the external account. Without this step, the shared snapshot, though technically visible, would remain unusable to the receiving account due to lack of decryption access. Once the KMS permissions are correctly configured, the encrypted snapshot can be securely shared from the production account to the QA or staging account. In that target account, the snapshot becomes available, and because the encryption key is now accessible, it can be decrypted and restored into a new RDS instance. Throughout this workflow, encryption is never removed or bypassed. The data remains protected from end to end, while at rest, during the transfer, and at the point of restoration. KMS key management is central to the security posture here, ensuring that only authorized accounts and users can access or restore the data. This cross-account sharing method is commonly used when teams want to test or troubleshoot production data in isolated environments, without compromising on data security. It's also a powerful way to replicate production environments for development and quality assurance while maintaining strong compliance and governance controls. Backups are critical, but if not managed properly, they can quietly become one of the biggest performance bottlenecks in your RDS environment. First, let us focus on backup window throughput optimization. Choose off-peak windows, align storage types with IOPS needs, and avoid general-purpose storage for write-intensive workloads during snapshots. For large volumes, consider provisioned IOPS SSDs to minimize backup duration. You can also temporarily boost storage throughput by increasing provisioned IOPS ahead of known backup windows. AWS allows elastic scaling. Use it to speed up backups, then scale down to control cost. If you're managing multiple databases, be wary of concurrent backup operations. Simultaneous snapshots can saturate I/O and network channels, amplifying latency across workloads. Stagger operations where possible, especially in high-throughput environments. Next, let's talk about I/O credit management for burstable instances like T3 or T4. These instances accrue CPU and disk credits during idle periods. Schedule backups when credits are high, or preemptively switch to unlimited mode during backup windows to avoid unexpected throttling. For mission-critical systems, read replica offloading is a powerful strategy. By backing up from replicas, you isolate production workloads from snapshot-related I/O suspension. Just ensure replicas are fully synced and meet your data consistency requirements. Don't forget network bandwidth allocation. Backups, especially cross-region ones, consume egress capacity. Monitor ENI bandwidth usage and segment traffic using QoS controls to avoid contention with application traffic. Use real-time resource monitoring to keep an eye on things. Build CloudWatch dashboards that track write IOPS, freeable memory, CPU utilization, and backup window length to detect anomalies early and tune configurations accordingly. Finally, consider workload scheduling around backup windows. Defer batch jobs, report generation, and reindexing tasks that could collide with backup I/O demands. A little coordination goes a long way in preserving both data integrity and performance. Restoring a database isn't just about rolling back to a snapshot. In today's enterprise environments, restore operations must be surgical, scalable, and smart. Let's begin with partial database restoration. While RDS doesn't natively support table-level restore, techniques like logical dumps with pgdump for PostgreSQL or MySQL dump for MySQL allow you to extract and restore specific schemas or tables. Then there's cross-engine restoration. Think migrating from Oracle to PostgreSQL or MySQL to Aurora. While not a direct snapshot restore, this involves schema translation, data type mapping, and often logical dump and reload. Tools like AWS DMS can facilitate real-time replication post-restore to bridge engine differences during migration. For schema-only restoration, dump utilities can extract just the DDL, ideal for setting up dev or test environments. This keeps environments lightweight and fast to deploy while preserving structural fidelity. You can also restore to different instance types. This is key when scaling for recovery testing or offloading analytics workloads. Start with a lower-tier instance, validate, then scale up or down based on performance benchmarking. For multi-phase restoration in petabyte-scale environments, break the process into steps. Restore metadata and core tables first, validate integrity, then parallelize restoration of less critical partitions or archives. This phased approach minimizes business impact. Don't overlook network configuration during restore. Restored instances may default to old security groups or subnets. Update routing, DNS, and VPC associations to fit the new environment context immediately. Finally, after a point-in-time recovery, there's often a gap. Use data synchronization techniques such as replaying logs from external systems or using DMS for delta replication to bring the database current with minimal data loss. Not all database engines are created equal, and neither are their backup behaviors. Starting with PostgreSQL, we have the powerful concept of wall archiving. Write-ahead logs. In RDS, you can enable wall keep size and archive mode to supplement standard snapshot-based backups with continuous, fine-grained transaction log archiving. This is essential for achieving high-resolution PITR and supporting complex recovery flows in dynamic workloads. Moving to MySQL, effective binary log management is key. RDS uses these logs for replication and point-in-time recovery, so tuning parameters like binlog expire log seconds and enabling row-based format enhances backup precision without bloating log storage. It's all about balancing granularity with cost. With Oracle, you may be familiar with RMAN, but in RDS, usage is limited. While direct access to RMAN is restricted, Oracle's recovery features are abstracted into the snapshot and archive log layers. For SQL Server, native differential backups aren't directly exposed in RDS. Instead, AWS relies on volume-level snapshots. This means restore operations always occur from full snapshot baselines, no incremental restores. Proceed with caution when performing engine upgrades. Engine version upgrades can alter backup formats and compatibility. Before upgrading, always ensure a full snapshot is taken and validate that PITR and automated backups will still function post-upgrade. Then there's compression efficiency. PostgreSQL and MySQL snapshots tend to compress well due to their storage engines, whereas SQL Server and Oracle, depending on block format and usage, may yield lower compression ratios, impacting storage cost. Finally, transaction log management differs by engine. MySQL uses binary logs. PostgreSQL uses WAL. SQL Server uses LDF files, each with unique implications for retention, I/O, and PITR. In modern data architectures, backups are no longer just an insurance policy. They're a strategic data integration point. We start with snapshot to S3 export pipelines. Amazon RDS allows you to export snapshot data directly to S3 in Parquet format. By automating this process, perhaps post-backup window, you create a seamless bridge from OLTP workloads to your data lake. Then there's change data capture CDC from transaction logs. By parsing MySQL binary logs or PostgreSQL WAL streams, you can build near real-time pipelines that capture incremental changes, even in sync with your backup cadence. Query federation is where things get exciting. Tools like Amazon Athena or Redshift Spectrum can query S3-based backup exports side by side with live RDS data. This enables unified access patterns across hot and cold data, ideal for analytics, compliance checks, or historical comparisons. Use backup-driven ETL to your advantage. Each backup completion event can trigger extract transform load ETL workflows. Whether it's an AWS Lambda or step function, you can align data freshness with backup cadence. Metadata integration is critical for governance. Export backup metadata, timestamps, table mappings, retention into your data catalog using AWS Glue or custom tagging frameworks. This ensures your analytics and compliance teams have full lineage visibility. Leverage data historization through PITR chains. By restoring snapshots to specific time points and extracting deltas, you can reconstruct time series datasets for trend analysis and anomaly detection. Finally, perform cross-environment consistency checks. Regularly validate your data lake or warehouse reflects the source of truth RDS state, using hash comparisons, row counts, or even query diffs. This ensures your pipelines remain trustworthy. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.